Alright, so we are going to touch on the next strategy of addressing the idea of recommendation retrieval. So what we brought up earlier in the part 1, just to bring us back to the original problem formulation, is that for recommendation problems, often we have to solve two phases of recommendation formulations. One during the learning phase, which is to learn the representations for users and items. They will allow us to estimate their preferences. Now in the second phase, which is on the retrieval phase, given a user, so for a known user, given a user, we would like to retrieve the top k most relevant items for that user. Now the challenge, of course, is the number of items. There are too many of them, and we want to achieve this retrieval very fast, like 100 milliseconds if possible. Now the first strategy, so we talk about the different strategies. So Andrew earlier has explained different ways to do approximate maximum inner product search. Essentially, a lot of them have something to do with processing the preference vectors that you learn from the learning phase in order to optimize them for use in the retrieval phase. Now, which means that essentially the earlier scheme is going to be solved in two stages. First, learn it, and then make sure that in the retrieval, the representations that we get in the learning phase is going to be appropriate for the retrieval. Now, we are now going to discuss a second strategy, which is what we call the indexable representation. Now, the indexable representation comes down to the idea that if the representation, if we know beforehand that we want to learn these preference vectors that we are going to use for retrieval. Now, if we know beforehand, why don't we learn a representation that is going to be natively indexable? Just make sure that at the point of learning it is going to be compatible with the different indexing schemes. Now, this essentially comes from two main schemes, and they are coming to the idea of Euclidean distance as well as indexability based on both Euclidean and Cosine similarity. Now, we are going to take a look at each one of them. Euclidean embedding is the idea of taking data points and embedding them within a Euclidean space. Euclidean space is a space that essentially obeys the triangle inequality, and in this space it behaves like a physical space. So a lot of the indexing schemes that have been developed in the databases, things like spatial trees, space partitioning trees, are going to be applicable immediately. Now, the second strategy is to do this a bit more generally, because Euclidean embedding requires us to change it to a different representation, which is Euclidean coordinates. But we are so used to working with matrix factorization and latent vectors. So another possible solution is to still keep the inner product formulation, but we are going to put some constraints on the inner product so that this inner product is going to still be compatible with both Euclidean nearest neighbor search as well as cosine similarity search. Now, we're going to begin with Euclidean embedding. Now, the idea of Euclidean embedding is to put items and users into a coordinate space. Now, because they're Euclidean, we have a physical feel for it, like a spatial feel for it, in the sense that if you want to get a sense of whether a user likes an item, just see how close they are in space. Now, in this case, for example, the users are circles and the items are triangles. So we are going to learn these coordinates that places users and items in the same Euclidean space, so that if you want to see the items that the user is going to like, you just see the nearby items. So for example, for this user, it's close to this triangle, so this user is going to like this item, but it's far away from this triangle, so this user probably will dislike this item. So this is very intuitive, because essentially it comes down to the notion of distances, and the closer they are in this space, the more likely that the user is going to like them. Now, to do this, we're going to contrast the original matrix factorization approach as well as the Euclidean embedding approach. Now, earlier, when we talk about matrix factorization, it comes down to the following representation, where we're going to learn inner product. We're going to learn latent vectors for user u, which we call xu, and the latent vector for item I, which we call yi. Now, the inner product of both of them are going to is going to give us the rating prediction. Now the other factors here are bias factors. We're not going to go into them for the moment. Now just pay attention to the inner product formulation. Now let's say in this case, this user U is this green circle in the middle here, right? And we want to know which items is the user going to like. Now we are going to ensure that they're going to have a high inner product. Now which means that anything with a large magnitude in the same direction as the user may actually be a candidate, which means that the search space essentially is very large. And in this case, we are not going to be able to cut down the number of candidates very fast. And in fact, we are still going to be searching across a large number of candidates. Now, in contrast, this is a Euclidean embedding formulation. Now, the key difference here, you see, is this notion of distance. Now, we're going to express the user's preference for an item in terms of the Euclidean distance between the two. In fact, here we use the squared Euclidean distance. By the way, this is a paper in Rexis 2010. Now, this squared distance implies that the smaller the distance, the higher is the rating between the user. Now, what it means is that given a user, if we want to know which ones the user is going to like, we just need to see the nearest neighbors. So in this case, if we define a radius and draw a circle around the radius, those are going to be where the candidates are. Now, of course, in this case, there is only one, but you can always have a slightly larger radius that is going to introduce more candidates, but it's still going to be a confined space where you have essentially narrowed down the search space significantly. Now, in this paper, the authors essentially showed that using Euclidean embedding, they can achieve pretty much the same level of accuracy as the original matrix factorization. So matrix factorization and Euclidean embedding, the precision and recall numbers are very close. And in fact, even in terms of learning time, is still pretty close as well. But the advantage of the Euclidean embedding is that you can apply a lot of the techniques that have been developed for nearest neighbor search in spatial databases to solve the problem. And in this case, the key advantage that we get is that of time. All right. Now, this is defined again in terms of explicit feedback. So remember what we said about explicit feedback earlier. They are essentially direct expressions of preferences which are clearly stated. These are things like ratings or thumbs up, thumbs down. Now, a different way of doing this is what is implicit feedback. Now, earlier we talked about BPR, which is the matrix factorization equivalent for implicit feedback. And over there, the optimization function is to make sure that the inner product for any given triple of Uij, where user U prefers item I to item J, we want to make sure that the inner product of Ui is going to be higher than the inner product for Uj. Now, if this is in the inner product space, so transforming this into the Euclidean space, there is a technique that is called collaborative ordinal embedding. This is a paper by us. We published it in SDM 2016. Now, the idea behind this is to look at the triples. And instead of saying that to satisfy the triples, you want the inner product to be higher, we are going to say that to satisfy the triple, we are going to make sure that the item that is preferred is going to be placed closer to the user. So in this case, we look at the distance between U and I, as well as the distance between U and J. And the distance between U and I, which is preferred, is going to be smaller than that between U and J. And by satisfying these triples across all the observations, we hope to achieve a better sense of top K retrieval, while at the same time placing the coordinates in the Euclidean space so that we can still enable K nearest neighbor search. Now, this is another advantage of Euclidean embedding. So one of the things that we talked about earlier is the idea of interpretability or explainability. Now, most of the time, we just see the latent vectors. They are very hard to understand in terms of what factor actually means, why some user and items are similar in certain kind of factors. Now, but Euclidean space is something that we human can relate to, because Euclidean space is the same space as the physical space. So distances make sense to us, which means that once we learn the Euclidean coordinates of the users and items, not only are they useful for the purpose of predicting ratings and preferences, or the top tier ranking, they are also useful for visualization. We can visualize them in terms of scatter plots. Of course, if it is higher dimension, we probably have to bring it down to 2 or 3 dimensions that we can visualize. But in the Euclidean space, we can then see the relationship between items and users. Now in this case, users are the triangles and the items are the crosses. We can present them in a space where people can appreciate if a user is closer to an item, then the user is more likely to prefer that item. Not only that, because of the collaborative filtering nature, because different users with similar observations, triples, they are likely to eventually end up at the same coordinates. We can then find which user is similar to other users. For example, these two are close together, so they probably are going to share similar preferences because they are close to similar other objects. Whereas this user, which is a little bit further away, is probably going to have a different in terms of certain movies. So for example, this is closer to these movies than to these other movies. Right? Now, so far, any clarification about Euclidean embedding? But the idea is that instead of matrix factorization, which is based on inner product, we are going to change the representation of user and items in terms of Euclidean coordinates. And this places them in the Euclidean space that allows us to use spatial indexing as well as other k-nearest neighbor techniques. Now, the second broad approach to doing this is what we call indexable MF, indexable matrix factorization. So, yes.
Like, do you think that maybe the Euclidean embeddings will break the effectiveness will break down in very high dimensions because of cursive dimensionality?
Because of the curse of dimensionality.
Like if like your space is so complex and you require like such a large space for your embeddings, then the like benefits from like the k nearest neighbors, all those like distance based metrics just break down.
So that's probably true, but at the end we are going to still use some level of indexing, and in the indexing scheme it will bring us down to a lower dimension. So which means that in the end, you still are going to decide that your tree is still going to be of limited height. There's still going to be some clustering effect. We're not going to use all the dimensions in the search all at the same time. All right, so for the indexable MF, which is matrix factorization, so here the idea is to still keep the matrix factorization formulation. So we're not going to change it to Euclidean coordinates. Instead, we maintain it as the original vectors. Now, the key idea is to ensure native indexability. And the intuition actually is very simple, as you will see soon. Alright, so let's talk about nearest neighbor search. Now, this is the contrast between the two. So for the maximum inner product search, which is the recommendation retrieval problem that we are trying to solve, given the vector xu, which is the query of a user u, we want to find the item I with the maximum inner product to the user u. Now, in the nearest neighbor search, which is frequently defined over the Euclidean space, the idea is that given xu, we want to find the item yi whose coordinate is closest to u in terms of the Euclidean distance. Now, if we expand this, so we see that the square root of the distance is similar to multiplying this to xu minus yi and xu minus yi. And this is going to generate into this following terms, which is the norm of xu, the norm of yi, as well as minus 2xu yi. Now, this component here is the same as the inner product here. Now, they are not equivalent because of the norms. So if the magnitudes of the coordinates are different, it's going to change which ones are going to be the nearest neighbors or the inner product. So which means that if we have a way to learn this in such so that all the items are going to have a constant norm, meaning then this particular term is not going to participate in the ranking. Now the xu, whether or not we keep it in a constant norm is less important because xu is the query. So it will not participate in the ranking anyway, because for all items it's going to be the same. So now the key part then is to keep the norm of the item vectors constant. And once we can do that, then the two problems are going to degenerate into essentially the same problem, so that satisfying one will satisfy the other one. So now all we need to do is to make sure that when we learn the matrix factorization, we are going to keep the item norm constant. Now, it's the same for cosine similarity, because this is the cosine similarity search. Now, it's still defined over the inner product, but the difference is that cosine similarity, we normalize it based on the magnitude. So which means that if the magnitude of yi is kept constant, so again it will stop participating in the ranking. And if it doesn't participate in the ranking, then the top k that you generate based on the cosine similarity will still be the same as the top k that you generate based on the inner product search. So if you can achieve this one simple objective, which is to keep the item vector norm constant, essentially we have come to a matrix factorization that is going to be indexable. And there are a couple of such formulations. Now, in this case, one formulation, which is making the probabilistic matrix factorization, or PMF, indexable. This is published by the following authors in Preferred.AI 2016. Now, the objective of the matrix factorization is still exactly the same. The only difference is the constraint. So in this case, there is a special constraint that makes sure that all the item vectors have a norm set to a constant c. And as long as we learn using item vectors such that this constraint is met, then we would solve the indexable problem. Now, how do they achieve this? They achieve this essentially by extending upon what we call Bayesian PMF, or BPMF. And in the case of the PMF, in the case of the original PMF, actually this should be Bayesian probabilistic matrix factorization. Every item and user vectors are drawn from a prior. And the prior is Gaussian prior, which means that any values are going to be possible, both positive and negative. Now here, in the work in Preferred.AI, they propose a method called IPMF, Indexable Probabilistic Matrix Factorization. The key idea is to change the prior from Gaussian to a spherical prior, which is called the von Mises-Fisher distribution, or PMF. This PMF distribution is defined over spherical vectors. So it means you can imagine that the space is now a sphere. Anything outside of that sphere of a given radius is going to be given probability mass of 0. So on the surface of the sphere, we are going to define a distribution based on some mean, and the mean is the mu, as well as some standard deviation. And the standard deviation is going to see, or given a spherical direction, how far away from there the items are going to be distributed. Now, by having this constraint, then all the item vectors that we are learning are going to be spherical vectors. They are all going to have the same radius, or same magnitude, which makes them then indexable. And indeed, the authors did experiments which are similar to the one before, showing that whether you learn the original PMF, which is a BPMF, or you learn the indexable one, where they keep the norm constant, the accuracies in terms of the RMSE are actually rather similar. So meaning you don't actually lose a lot in terms of accuracy, but you gain an advantage in terms of indexability. Now, this is an example of the BPMF versus IPMF by using a few different indexing schemes. So there is a KD3, there is a k-means 3. So k-means 3 is similar to KD3, except that when you split in the binary search tree, you first do k-means clustering to divide them into the different clusters. And then the LSH. Now we're going to compare them controlling for the indexing schemes, so that we are comparing things that are only affected by the algorithm. So the green one and the black one, for example. So the green one here is the BPMF with the KD3, and the black one, the circles here, are the IPMF, the indexable one with KD3. So if you look at this, this is a speed up compared to exhaustive search, like the linear scanning. This is how much faster you go, and this is in terms of the precision. So we see that using the IPMF, we get higher precision for the same speed up ratio. And in this case, you can control for the speed up and get a higher accuracy, or you can control for the same accuracy and get a higher speed up from the indexability, which gives you an advantage in terms of retrieval. This is similar, but expressed in terms of a different metric, which is RMSE. Previously, it was precision. And essentially, the advantage is still the same. In this case, RMSE lower is better. So the one with the KD3, the BPMF, which is not indexable, has higher error than IPMF, which is indexable. Now, this is done for explicit feedback, which are ratings. So there is another kind of strategy, which is also about making it indexable, but we are going to rely on implicit feedback. Now, originally implicit feedback, we talk about BPR instead of PMF. BPR is Bayesian personalized ranking, still about satisfying triples, like user item I, item J. And if user U prefers item I to item J, we would like to satisfy the triple by making sure that the inner product of UI is larger than the inner product of UJ. Now, but because it's based on inner product, again we have the same problem, where the norm is going to interfere with the indexing schemes. So if we apply the same principle and keep the norm constant, or at least find a way where the norm doesn't participate in the ranking, then we can ensure that the matrix factorization will still be indexable. Now, this is again we're making BPR indexable. So this is original BPR objective function, which is to satisfy the triple by making sure the inner product is higher than another. This is another piece of work which we published in CIKM 2017, Indexable Bayesian Personalized Ranking, or IBPR. Now here, instead of using it in a product, what we are going to be comparing is the angular distance. So in this case, we take the cosine similarity, the inverse cosine will then be the angular distance itself. We make sure that angular distance is going to be smaller for an item the user U prefers than to another item J, the user U prefers less. Now, because in the angular distance, as you see, the magnitudes do not participate in the ranking because we would have normalized the norms. In that case, when we are ranking them, the ranking by the angular distance is going to be similar whether we do it in a product space or whether we do it in the cosine space. And as a result, there is a general indexability, and you can use this technique essentially for almost any kind of indexing, including LSH, spatial trees, as well as inverted index. Now, we look at a few experiments. This is on Netflix data. Now, the methods being compared here, so the red line above is IBPR, and this is based on LSH. So LSH is, you have to decide how many hash functions, which will give you the length of the hash code. Now, the longer the hash code, which means you go from 4 bits to 8 bits to 12 bits to 16 bits, the longer the hash codes, then the cell, you're going to have more cells in the hash table, but within each cell, there are going to be fewer items. And because there are fewer items, you are going to achieve a higher speedup. But because the LSH is approximate in terms of the similarity, you might also reduce in terms of the accuracy. And that's because some of the items may end up in a different cell in the hash table, instead of the cell in which the user actually falls into. Now, but IBPR, because it's based on the ranking, it does perform better than some of the other techniques. So for example, IPMF is the green one. IPMF optimizes for the ratings, which in this case, IBPR optimizes for the triples or the rankings. And it does better in terms of the top K ranking. Now, this is for working with LSH. Now, if you apply this, but apply it to the KD3, so again, there is some similarity here in the case that IBPR still performs better. And you can control the resolution of the search by looking at how many nodes in the binary search tree that you're willing to visit in order to find the closest items. And the last one is with inverted indexing. Andrew earlier has explained this scheme where you can sparsify the vectors. So you can go higher dimensional and create a sparse vector that will allow us to use inverted indexing. And here in the same sense, right, this is going to be the resolution of that sparse vector. And at higher resolution, we are going to have a higher speed up, but at the same time, we are going to have a slightly lower accuracy. But in this case, the indexable method is still going to outperform the matrix factorization that is less indexable. Now, that's essentially the idea behind the second approach. To achieve indexability, we have two different ways to do it. One is to transform it into a different representation, which is Euclidean coordinates. If we do that, then we can employ k-nearest neighbor techniques to solve the retrieval problem. Now, probably something that is more comfortable to a lot of recommendation folks is to keep the idea of matrix factorization, but make it indexable. And it turns out that the principle is simple. Just keep the norm of the items constant, and then you achieve indexability. But of course, it's not trivial to achieve that because it depends on the specific algorithm. Yes.
So in the case of like cosine similarity,
Yes.
so would embedding the same as using Euclidean embedding?
So in the case of the cosine similarity, you still maintain the inner product formulation.
But the inner product formulation actually could be expressed as like the sum of the norm of two vectors minus the cosine similarity, right?
Minus the cosine similarity, that's right. So in that case, this is this one, right?
Yeah, so so because norm is constant, right?
Right.
So this cosine similarity, the Euclidean distance is essentially the same as cosine similarity.
It will also be the same as the cosine similarity, that's right.
Right, so actually these two approaches are the same.
These two approaches are the same. Well, they are going to be different in terms of the objective function that they are trying to achieve.
The objective function actually are the same because Euclidean distance equals like a constant minus the cosine similarity.
It's not exactly, because if what we want to achieve is ranking, that means if you express your objective function in terms of the ranking, then it will be the same ranking. But sometimes it's defined in terms of the rating, which means that you're trying to estimate actual values. In that case, whether the distance is the rating, or whether the cosine similarity is the rating, then you're going to get slightly different functions. That is going to be a little bit different. All right, I think this is basically the second strategy of making the representation indexable.